this is the continuation of the previous lecture. In this lecture, we will see how to write the dynamic equation of a n degree of freedom manipulator. So, in the last lecture we have seen how to write the dynamic equation of a 2 degree of freedom manipulator with uniformly distributed mass. So, here we consider a general n degree of freedom manipulator whose arm matrix is written as 0 Tn which is the product of 0 T1, 1 T2 etc. So, in general this I minus 1 Ti, it represent the coordinate frame of the ith joint with respect to the I minus 1th coordinate frame. So, if you consider a general robot manipulator with n degree of freedom, so the so if you consider the 0th frame as x0, y0, z0, that is the base coordinate frame, and xn, yn, zn is the end effector coordinate frame, then 0 Tn it represent the the tool frame, end effector frame with respect to the base frame given by this, and then it is already known from the DH algorithm that I minus 1 Ti can be written like this. So, if the ith joint is a revolute joint, then theta I it represent the joint angle, it is a variable. In case ith joint is a prismatic joint, then theta is a constant and di is a variable in that case. Now, the differential transformation D represent a matrix which contains dx, dy, dz and del x, del y, del z, which are the translational and rotational velocities of a particular joint with respect to the base frame. And here d superfix t, it represent the translational and rotational velocity with respect to its own the current frame, the t frame itself. So, in the Jacobian lecture we have seen the relation between d and dt through the arm matrix. So, now if we denote I minus 1 Ti as T suffix I, then the derivative with respect to the variable Qi, because the ith frame is a function of Qi, where Qi is either theta I or di, depending on whether the ith frame is a revolute joint or prismatic joint. So, the derivative with respect to the ith variable Qi, the partial derivative is given by d suffix I into Ti, where d suffix I is this matrix if it is a revolute joint, or this matrix if it is a prismatic joint. So, the partial derivative with respect to the variable is given by di multiplied by the matrix T suffix I. So, the total derivative dt by d small t is given by the standard chain rule del t by del q1 into q1 dot plus del t by del q2 into dq2 by dt etc. is the total derivative of the matrix T, where del t by del qa is given in the previous slide. Now, if you consider 0 Tj, the jth coordinate frame with respect to the base frame, which is given by this product. And if you denote ujk means the partial derivative of 0 tj matrix with respect to the variable qk. Because 0 tj, it contains 0 t1, 1 t2, j minus 1 tj. So, when we differentiate 0 tj with respect to a variable qk, where k is less than or equal to j, we get, because the derivative is effective only with the matrix tk. And in the previous slide we have seen that the partial derivative of tk with respect to qk is given by dk multiplied by tk. So, by substituting that we get the derivative to be like this, in this way. Now, if we further differentiate ujk with respect to ql, where L is say less than or equal to j again, then we can denote it by ujkl. The notation ujkl means we differentiate ujk with respect to ql, that is. So, it is very clear that once again if you differentiate this term del by del ql, then wherever t suffix l appears, that derivative will be effective in that place. Whether it is after tk or before tk, wherever tl appears, the derivative should be effective on that tl. The derivative will be d suffix l into, so this is del tl by del q suffix l. So, depending on whether it is revolute or prismatic, this matrix D can be selected and substituted. So, for example, if you have u j k l, it is if j l is less than k, this d l t l will appear before d k t k, or if l is greater than k, then it will appear after this tk. So, in all the cases we can write ujkl notation to be the partial derivative. Now, let us assume that P be a point on the jth link with respect to jth link. So, if you consider the so for example, let us say this is the first link and this is the second link, and the coordinates are x0, y0, z0, and if you assume this is the rotation with respect to z1, the revolute joint, and we can fix the x1, y1. So, if you consider this is the point O, this is the point A, and so we have two coordinate frames x0, y0, z0, and here we can fix x1, y1, z1. Now, if I consider this is the first joint, this is joint 1 and this is joint 2. So, if I write the joint 1 with respect to the first frame, similarly jth joint with respect to jth frame, it means the link is, for example, here this is the first link and the first coordinate frame is z1, x1, y1, etc. that can be fixed. So, with respect to x1, y1, z1, the link 1 is considered. Similarly, if you have another joint, for example, here z2 and x2, y2, etc. can be fixed. So, with respect to x2, y2, z2, the link 2 is written. So, we take a point P, general point P on the link 2 with respect to x2, y2, z2. Similarly, here according to this, let P be a point on the jth link with respect to the jth coordinate frame. So, that is the meaning here. So, now let Rj denote the vector representing the point P in the jth coordinate frame. So, if you take a particular point P on the second frame and write the vector with respect to x2, y2, z2, it is this vector. This is the R2 vector. We can say that with respect to the x2, y2, z2 frame for a particular point on the second frame. Similarly, if we take a point P on the jth link with respect to jth frame, its coordinate vector we call it as R suffix j here. Now, the same point, the point P if you write with respect to the base frame, that is called Pj, the point with respect to base frame. So, for if Rj is the a vector with respect to the jth coordinate frame, then if you multiply in the left side by 0 Tj, it represent the same point with respect to the base coordinate frame. So, Pj represent the point P with respect to the base frame. Now, the velocity of the same point means we have to differentiate the vector Pj with respect to time. So, d by dt of 0 Tj into Rj. So, we always keep it in mind that Rj is a fixed vector quantity and 0 Tj is a function of q1, q2 up to qj here. So, we have already seen that the derivative d by dt of 0 Tj, how to write it? It is through the summation. In the previous slide, we have seen already the derivative del by del qk of 0 Tj for different value of k. So, that is substituted here because it is a total derivative. In terms of the partial derivative, we will write the summation k equal to 1 to j of del by del qk of this into the dqk by dt. So, it is the same formula as given here, the total derivative this thing. Instead of n we have j here, that is the only difference. So, multiplied by Rj. So, by using the notation ujk, we can write this can be replaced by ujk. Now, the point P, one point P is considered if the link is with uniform mass distribution, then at a point P we take a length dl, a small element of length dl is taken. So, if rho is the uniform density, then the kinetic energy of a element of length dl is given by half into mass is rho into dl into velocity square. The velocity of that element is v and its square, modulus of velocity can be taken. So, the kinetic energy of the small element of mass can be calculated by this formula. So, how to calculate that? We take the point P to be xj, yj, zj with respect to the base, and Vj is given by x, its derivative is xj dot yj dot zj dot, and Vj is a column vector, Vj transpose is row vector, the same thing. If you multiply Vj and Vj transpose, we get xj dot square, xj yj dot and xj dot zj dot etc. So, directly multiplying Vj and Vj transpose is this. Now, the trace of this matrix is the sum of the diagonal elements, that is xj dot square plus yj dot square is zj dot square. That is the velocity modulus of the velocity square. So, in the place of modulus of velocity square we replace by this trace of Vj transpose. So, the kinetic energy of the small element dk is half into trace of this is Vj into this whole thing is Vj element and then its transpose Vj transpose. Now, if you multiply two summations here it varies from 1 to j. So, there are double summation. So, we replace one variable we call it as k and another variable is called as L here. So, k varies from 1 to j and L varies from 1 to j, and if we take transpose of this matrix, because R is a vector and here U is a matrix, Q is a number, it is a joint variable, Q dot is the velocity. So, it is a number here. So, U, when we take the transpose of the product of two matrices, here it is U j k and R j multiplied by this Q k dot is there. If we take transpose of this one, and because this is simply a real value, we take the transpose of this two, it is R j transpose U j k transpose. So, by using that transpose property, we can write this product as double summation k equal to 1 to j and L equal to 1 to j of U j k is this, and here R j is as it is. Then we get R j transpose as we are using this one, then multiplied by U j L transpose, the transpose of this one, multiplied by these two real values Q k dot Q L dot, multiplied by this small mass here, because rho into dl it is the small element mass dm. Now, we can calculate the total kinetic energy of the jth link. It is the total integral. If the jth link has length let us say Lj, then we have to integrate from 0 to Lj, because we have taken small element mass length dl, and if you integrate from the total length from 0 to L, we get the total kinetic energy. So, we get the same formula can be integrated. The integration is effective only on this Rj and Rj transpose, because Rj is the vector in the jth coordinate frame, which is a constant vector. Similarly, Rj transpose is a constant vector. We multiply this two and then integrate from 0 to the length of the particular link. So, now we can write Rj transpose is given by this expression x j square. If I write the vector Rj to be x j y j z j, then with respect to the jth frame. Now, if you multiply Rj transpose, we get this expression, and if you integrate from 0 to the length of the particular link, we get this expression. So, for example, if you integrate x into y into the length dl 0 to the total length, for example, that is given by Ixy, the inertia with respect to the xy plane. Similarly, if you integrate this, it is the inertia with respect to xz, and the because normally in homogeneous transformation a vector is represented by 4 values. The first 3 represent the coordinate and the last one is a dummy variable 1. Okay. So that in the first lecture we have seen how to write the coordinates. So Rj is, so here the sorry, we have to see that everywhere we should write 1 here, so that it is a homogeneous coordinate vector. Okay. If we differentiate 1 we will get 0 etc. So we get here 0 0 0 etc. Here also the same thing, R is represented by x, y, z and 1 here in the end. Yeah. So when we do the integration we get inertia with respect to xy plane and here inertia with respect to xz plane. When we integrate this one, the last one with respect to 0 to L dl, this will give the mass, the total mass of the link multiplied by the, because we know that integral x into dm multiplied by the uniform density, this gives the value of the x coordinate of the center of mass of that particular link multiplied by m here. So we get this one integral of x into dm, it represent mass into the center of mass x coordinate. Similarly, the integration of this will give mass into the center of mass of the y coordinate of the center of mass, and integral L is the z coordinate of the center of mass multiplied by m. So the same thing is repeated here, and here also we can easily see, the next slide we can see that Ixx, it is nothing but the inertia with respect to the x axis. If you take any point P, if you drop a perpendicular, so this perpendicular to the x axis. So this is nothing but y square plus z square. If the point P has x, y, z as the coordinate, the length of this point, if we drop a perpendicular to the x axis, the length of PM is nothing but y square plus z square, length square. So this gives the inertia with respect to the x coordinate, and x square plus z square is the square of the distance from P to the y axis. So this gives the inertia with respect to y axis, and this is inertia with respect to z axis. So we can easily see from this one, the calculation, the integral of only x square if we take into dm, that is given by this expression. If you substitute for Ixx, Iyy, Izz from this quantity divided by 2 will give only the first integral. So simply the integral of Rj transpose is given by this matrix, which is called the inertia matrix. This is a fixed one because Rj and Rj trans, they are not going to change throughout the motion of the robot manipulator. So once a robot manipulator is given, for each joint, each link j, we can calculate the inertia matrix, and it is a fixed one. Now the total kinetic energy is summation of all kinetic energies for the link 1 to n. So we can simply write that the kinetic energy for the jth link is this, and we are summing up all the, so it is j equal to 1 to n for all the links, and the next two summation it gives the formula which we have given, the kinetic energy of the jth link. And this expression, it is nothing but half into the inertia of the jth actuator multiplied by qj dot square, the velocity square. So, if the actuator, jth actuator is a revolute one, if it is revolving with velocity qj dot, then qj dot square multiplied by the inertia of that actuator, it gives the kinetic energy of that particular actuator. So, now if you add the kinetic energy of all the actuators, we get this formula. So, total kinetic energy, these are the link kinetic energy, and then this is link kinetic energy, and these are the actuator kinetic energy. Similarly, we take potential energy. Potential energy of each link can be calculated as mass into gravity into the height. So, if you take a particular point on the link, this point, so the height to be calculated with respect to the base actually. We have to consider. So, the base is this one and the jth link, we let us say this one. If P is the point, we have to write the gravity vector will be pointing downwards, and the height is from the point P to the projection of the point in the xy plane. So, we have to calculate. So, the gravity with respect to the frame we have to write. So, the kinetic potential energy is given by mass into the gravity vector with respect to the jth frame, because we are considering the potential energy of the jth frame. So, if the jth frame is in different orientation, let us say, because throughout the robot motion the frames are moving in different orientation, but the gravity is always pointing downwards. So, when we write the gravity vector in the jth frame, then it will have 3 components. Okay. It is a vector represented in the jth component, it is a constant vector. So, mass into gravity into height, the height is given by 0 Tj into Rj. So, the gravity vector dot product the P vector, Pj vector with respect to the base frame. So, that gives the height. Okay, this will give modulus of the gravity vector, and this is modulus of Pj into this thing, cos of the angle between these two vectors. So, it means it is the projection of the gravity vector on the perpendicular vector. So, it gives mass into gravity into height type of thing. So, this gives the potential energy formula. Now, if you write the Lagrangian, that is kinetic energy minus potential energy of the entire system. So, we can write collect the kinetic energy, collect the potential energy, and then take k minus p, that is the L Lagrangian. So, after this we can simply write the equation of motion, that is d by dt of del L by del q j dot minus del L by del q j equal to tau j. If it is prismatic, or f j, if it is revolute, it is torque, if it is prismatic, it is the force. So, the equation of motion can be written from the Lagrangian formula here. After doing all the derivatives, we can obtain the dynamic equation of this problem, which is a very lengthy process. As it is seen here, there are too many summations and too many variables are there. If it is a n link manipulator, so it is really a very lengthy procedure to get the dynamic equation of the n arm robot manipulator. So, this lecture gives only the procedure to find the Lagrangian of the manipulator, and the remaining can be calculated using this formula. Okay. Thank you.